This video is another tutorial on the digit management system. In this one, I will explain how to create and query our three-dimensional relational database tables. It is particularly important because it highlights a few of the fundamental differences between our system and other conventional database systems. So let's start off with a simple customer table. Here on our Databases tab, we'll have a definition for a table with 10 columns. As you can see here, it has 10 columns with names, addresses, etc. The zip code has a number, but all the others are strings. Now, out in our file system, we have a simple file called customers1 in JSON format. If I pull it up in an editor, you'll see that it's just an array of customer records that match the definition. Each record has one and only one value of the proper data type for each column in the table. So this file, like a CSV file, contains highly structured data, and it should be easy to import into a single table in almost any database. We make that really simple to do in digits. Just drop that file onto the definition and import the data, and it makes a table that can be easily queried by simple SQL statements. Here we have just 10 records in here of names, addresses, city, etc. Now, the problem for most other systems is what to do when your data is not so highly structured. For example, what if a customer has more than one phone number? Conventional database systems typically store each row in the table within a fixed size record. Each record has room for only one phone number. In the comment section for this video, I outlined 4 options available on other systems and the drawbacks for each option. The options include making the phone column space bigger and putting multiple phone numbers in that space, adding a column, duplicating the rows for customers, or creating a separate phone table that you have to join each time. Now, Digits makes it possible to add values to any column that is not a primary key without creating separate tables, wasting space, or doing costly join. Now, because each column in our database table within Digits is a separate key value store, we can map as many values to each row key as we want. This adds a third dimension or depth to any table. So let's add a phone to one of these customers. Come over here, highlight the customer phone number, and say we want to add a value to this. And we'll make it very simple. We'll just say 123. Now what that did is it added a second value, and you'll see that now for that key row, that row column value here, there's 2 values. If I double click on it, it'll show you both values, the original phone number that was in there, as well as the 123 we just added. Any columns that have at least one row in them with multiple values, we put the little array or brackets around the name so you can tell that it has multiple levels on this. So we could do that for any value in this table, and it creates a second dimension. So let's go out and now look at a customers to file where we've inside of the JSON, we've added a couple phone numbers to this record. We've added a second state to this record and a second name to that one. So now we have 3 records with multiple values. So if I take and drop that on that customer definition, now we'll create a customers to. And sure enough, this value has 2 rows in it, or 2 values, 2 names. This one has 2 states, and there's our 2 phone numbers. So again, we just double click on the value and we'll see both states that were in there. I can highlight everything, select them all, and say show the JSON, and you'll see that that record has 2 phone numbers, 2 states. I can export this back out or put it in the clipboard or do anything I want with it. Now let's say we want to add even a more complicated. So here we have a customers 3 JSON, and we've added a payment subdocument to each one of these documents. So this customer has a payment here. This one has 2 payments, so the payment is in an array. So this is assuming maybe we're a repair shop, and here's the appliance, and here's the amount to repair it, and there's the ID for the value. So you see some columns have no payments, others have up to 3 payments, and others only 1 or 2. Now, if I just drop that on this customer, which doesn't have any payment in the definition, it would ignore all those payments. So what we want to do is drag and drop it on an area in the definition here. Now, for a moment here, let's just keep the default and now create that table with customers 3. So now we have this customer 3, and you'll see it added the payment amount, payment ID, and payment items. And those customers that had 2, you'll see 2 levels here. Those that have 3 have 3 levels. And again, so here's the item. This guy had his television, oven, and blender all prepared. So any query using simple SQL to find every row with a blender, we'll see this row will come up because one of its values had a blender in it. So we made it very easy to pull that data in. Now the other option I want to show you here, what if we put this on here and say we only want to see payments? So what we do is we show you all the sub documents within there, and we want to make a separate table just out of payments. So we're going to set the new root, call this customers 3 with the payment subtype. And so now I end up with a new table that only has those 3, the amount, the ID, and the item. So I've basically created a table just out of those sub-documents across that entire array. The last thing I want to show you is we have a table here of 500,000 friends that we had previously dropped on a friends definition. You see there's 500,000 rows in here with cities, states, phones, and emails. What we did is after we did that, we modified this friends definition so that the city is a primary key. So if we look at the values here, there's only 1,046 unique city names in this table. So if we take that same file and drop it now on the definition with the primary key, it's going to ask us what do we want to do when there's a collision. And in this case, we're going to create new levels for the other columns. So it's going to create that third dimension. It's going to import all our data. It takes a few seconds to import all 500,000 rows. But when we're done, we should have a table here with only 1,046 rows in it, but it's going to be very deep because we have 500,000 records. We're going to map to those 1,000 row columns. So when this finishes, we're almost up to 500,000. There we go. And there's some duplicate things that it ignored, so it shows you that. But here now is our table in which, so the city of Rialto, there were 489 different names that map to that city. If I want to see all 489 of them, there they all are. And how many other rows in this table also map that. So this Marnie, England was seen 4 times in the table. So if I double click there, those are the 4 rows where that name appeared and the cities in which they're in. So we made it very easy to create. This is an atypical kind of thing. You probably wouldn't want to create this table with this kind of depth. But to show you that we can create massive tables that are very deep and do queries against them very quickly. And that highlights how where this key value store for each column in a table makes it very flexible to handle highly structured data and the semi-structured data. So you don't need a separate, no SQL solution in order to manage this data that is very flexible in its schema. Thank you very much.